This is a screencast on projectile motion. So what do we mean by projectile motion, first of all? Well, a projectile is any object which has a motion where the only force acting on that object is due to gravity. So for projectile motion we don't include air resistance, and there can be no other forces, either vertical or horizontal, acting on the object. The only force acting on the object is due to gravity. So let's take an example of that. Let's say we have a stone, and at this point the sum of the forces acting on the stone is equal to 0. So the weight force of the stone is balanced by the normal force of the stone. If that doesn't make sense to you, maybe it will when you watch the screencast on forces. And there are no other forces acting on the stone in the horizontal direction. However, the stone does have constant velocity, so it's travelling along with constant velocity. Remember, something travelling at constant velocity has no net force acting on it. So it's got a constant velocity of 5 meters per second, and it reaches the edge of the cliff with a constant horizontal velocity of 5 meters per second. So what happens when it rolls off the edge of the cliff? Well, if there was no gravity, then the stone would travel along at a constant horizontal displacement with a horizontal velocity of 5 meters per second forever and ever. However, because there's gravity, what happens is the stone will gain a vertical downward velocity. Okay? So if there was no gravity, it would travel along this line, which we call the zero gravity line. In reality, this is what happens. This is because the stone has both a horizontal component to its velocity and a vertical component to its velocity as it's rolling off the edge of the cliff. So initially at this point right here, it has no vertical component to its velocity. It's only got a horizontal component. The horizontal velocity is 5 meters per second. And as I said, if there was no gravity, it would travel along this line, this zero gravity line, forever with a horizontal velocity of 5 meters per second. So why does it gain a vertical velocity? Well, because of gravity. Remember we said projectiles are objects where the only force acting on them is due to gravity. So because of the force due to gravity, in other words, the object's weight, it will gain a downward velocity. So let's say that the time that it takes for it to hit the ground is 5 seconds. It's in flight for 5 seconds. At this point, as it rolls off the edge of the cliff, its horizontal velocity, or its velocity in the x direction, is equal to 5 meters per second. Its velocity in the y direction, the vertical direction, is 0 meters per second. What about at this point here along its path? Its horizontal velocity. What is its horizontal velocity going to equal to? Pause the video and think about that for a second. Think about what forces are acting on it in a horizontal direction. There's no air resistance. So hopefully you understand that if there's no net forces acting on it, its velocity will remain constant. In other words, its horizontal velocity, or its velocity in the x direction, will remain at 5 meters per second. But what happened to its velocity in the y direction? It will have gained some velocity in the y direction. Why? Because it has a net force acting in the downward direction. If there's a net force, it's accelerating. In other words, its velocity in that direction will increase. So it started out with 0 velocity in the y direction. Now it has some small velocity in the y direction. What about at this point? Its velocity in the x direction will still remain 5 meters per second, but now its velocity in the y direction has increased further still. As it reaches the ground, its velocity in the x direction is still 5 meters per second, and the velocity in the y direction has increased again. So it's because of this constant velocity in the x direction but increasing velocity in the y direction that you get this curved path. So that's why projectiles follow a curved path. So we can do some analysis on the stone as it tumbles off the cliff. The first thing we'd like to do is figure out what is its vertical velocity on impact. We know its horizontal velocity is 5 meters per second, but what's the magnitude of this vertical velocity Vy on impact? So the trick with projectile motion is to be able to separate an object's motion into vertical and horizontal components. In other words, when we deal with the vertical part of the object's motion, we completely forget about the horizontal motion. Okay? And that can be a little bit confusing. But if we forget completely about the horizontal motion, what is the stone doing vertically? Think about that. What the stone is doing in a vertical direction is it starts out at the top of the cliff with 0 velocity, and then vertically it travels straight down. So again, forget about the horizontal. What's happening is, as the stone falls off the edge of the cliff, it falls straight down vertically. It only follows this curved path because it also has a horizontal component to its velocity, but we're forgetting about that. We're going to deal only in the vertical plane. So in the vertical plane, what's its velocity at this point? It's 0 meters per second. What's its acceleration as it falls through the vertical plane? Well, the only reason it's accelerating is due to gravity. So its acceleration will be equal to gravity, depending on what value we decide to use for that. And what time did it take for the stone to fall? Well, the amount of time it took for it to follow its curved path is the exact same as the amount of time that it took to fall straight down if we take it vertically. And that's a time of 5 seconds. So we want to find the velocity, v, at this point. So we can treat this just like linear motion because we're dealing with it only in the vertical plane. So I'll get rid of this just to tidy this up, and then we'll answer the question. So if we were dealing with linear velocity, we'd choose a Suvat equation. So we're going to do the same thing here. We know that its velocity in the y direction is 0 meters per second. We don't know its final velocity in the y direction. Its acceleration in the y direction, we're going to take it as minus 9.81 meters per second squared. So I've chosen that down is negative in this case. And the time is 5 seconds. So looking at this information, pause the video, try to figure out which equation you will use to solve the question. So hopefully you chose the equation v is equal to u plus at, Suvat equation. But in this case, all these components are in the y direction. So it's vy is equal to uy plus ay times t. Why is it not ty? Well, because t is a scalar quantity and does not have any direction. Time does not have a direction. So I fill in my values into my Suvat equation, and I get that the final vertical velocity is minus 49.05 meters per second. And that confirms that the velocity in the y direction, the final velocity in the y direction, is downward, because I chose at the start, when I chose my acceleration value, that down would be negative. Okay, so that's that. So what if we want to calculate the vertical height? In other words, I want the height of the cliff. Okay, again, we're just dealing with the vertical component of its velocity here. The height of the cliff is equal to the vertical displacement that the stone travels. In other words, Sy. So we could use another Suvat equation. In this case, we're going to use S is equal to ut plus a half at squared. But these components are all in the y direction, so again, I have to phrase them in the y direction. So it's Sy is equal to uy times t plus a half ay times t squared. That should say ay. Okay, so again, I just fill in my values. You can see here that my initial vertical velocity was 0, so that cancels out that. Plus a half times acceleration. Be careful, make sure to include your minus here or you won't get the correct answer. Minus 9.81 times the time, 5, which is all to be squared. So I work out that my vertical displacement is minus 122.63 meters. However, the height is a scalar quantity, so I want the height of the cliff. So the height is going to equal to the absolute value, or the magnitude, of the displacement. Magnitude means without direction. Absolute value means that we don't care about positive or negative. Okay, we just want the magnitude. So the magnitude of the displacement in the vertical direction is 122.63 meters. That just gets rid of my minus sign. Another question. What if we wanted to calculate the horizontal distance traveled in those 5 seconds? So now we need to deal in the horizontal plane, and we're looking for this displacement here, Sx, the horizontal displacement, or displacement in the x direction. So how far will the stone travel horizontally in those 5 seconds? Now we forget about the vertical and we deal only in the horizontal. So we can use our equation, s is equal to ut plus a half at squared, but now we're dealing in the x direction. So it's sx is equal to ux times t plus a half ax times t squared. Let's think about what all these values are. What's ux? The initial horizontal velocity. It's the same as vx. It doesn't change throughout the motion. It's 5 meters per second. Remember, the horizontal velocity is constant throughout the motion. What's ax? The acceleration in the horizontal direction. Maybe pause your video and try to answer that question. So when you think about that, we said at the start of the question there's no air resistance, there's no forces acting in the horizontal direction, therefore there can be no acceleration in the horizontal direction. So the acceleration in the horizontal direction is going to be equal to 0. So we fill in our values, we cancel out the half at squared part of the equation, and we're left that the horizontal velocity is just equal to ux times t. The horizontal velocity times the time. And that gives us a value of 25 meters. What if we wanted to calculate the resultant velocity at the time of impact? So the resultant velocity means the resultant of this horizontal component and this vertical component. Pause the video, try to solve this question. So hopefully once you've covered vectors and vector addition and resolving vectors and resultant vectors and all that, this is pretty straightforward. We have two vectors, Vx and Vy. The magnitude of Vx is 5 meters per second. The magnitude of Vy is 49.05 meters per second. And I want this resultant vector. So, from Pythagoras we have, I'm just going to call the resultant vector V, okay, the resultant velocity. From Pythagoras we have V squared is equal to Vx squared plus Vy squared. In other words, the square of the hypotenuse is equal to the square of the components, or the square of the other two sides of the triangle. Therefore the velocity is going to be equal to the square root of Vx squared plus Vy squared. So I can find the magnitude of the velocity pretty straightforward. It's equal to 49.3 meters per second. But a resultant velocity needs a magnitude and a direction. So how can I work out the direction? I want to choose this angle below the horizontal to define my velocity. So I can use tan of theta is equal to opposite over adjacent. Tan of theta, what's the opposite? The opposite is this part here, Vy. 49.05 over the adjacent, which is Vx, 5 meters per second. And I get the tan of theta equals to 9.81. Theta equals 84.18 degrees. So my final answer is that the velocity equals to 49.3 meters per second at 84.18 degrees below horizontal. So this is a pretty straightforward question because it doesn't involve any initial vertical velocity. The problem started out with only horizontal velocity, no initial vertical velocity. So let's see what happens when we try a problem with initial vertical velocity as well as initial horizontal velocity. There's lots of examples of this. If you think about someone throwing an American football in NFL, for example, the person throws the ball with varying degrees of vertical and horizontal velocity. If they want the ball to travel very fast in a very straight line, then they throw the ball with a very large horizontal velocity but a very low vertical velocity. But if they want the ball to travel very far and very high at a slower speed or a slower velocity, then they throw the ball with a much greater vertical velocity but a smaller horizontal velocity. So another example of this would be a person shooting a bow and arrow. So the person here is standing at the top of a castle wall and they're going to shoot the arrow with an initial velocity of 60 meters per second. And that 60 meters per second is shot at an angle theta above the horizontal. So we'll say that theta equals to 30 degrees. The height from the ground that the arrow is shot from is 80 meters. And he's shooting at this poor individual over here who's trying to attack the castle. So what's going to happen? Well, the arrow is going to follow a projectile arc and eventually impact the other person. So let's say it's going to impact the other person at a height which is 1 meter above the ground, so somewhere in the chest. Bad day for him. So the first thing we want to be able to do is to calculate the maximum height reached by the arrow. All right? Think about what that means. It means this point over here. So again, we need to be able to separate the motion of the projectile into its vertical and horizontal parts. Its horizontal velocity is always going to be constant because there are no forces acting on it in the horizontal direction. What force acts on it in the vertical direction? Again, it's just gravity because it's a projectile. So, in the vertical plane, you can think about the arrow just traveling up, reaching a maximum height, and then back down past its starting point and continuing down until it reaches the height that it hits the person in the chest. So vertically, the arrow just travels up, reaches a maximum height, and falls back down again. So think about the different components of its motion when it reaches that maximum height. What's its acceleration throughout its vertical motion? It's always going to be the same. It's going to be gravity. What's its initial vertical velocity? Well, we'll have to work that out. And what's its final vertical velocity? When it reaches its maximum height, it stops for a second and then starts to fall back down again. So in other words, in the vertical direction, its final vertical velocity is going to be 0 when it reaches its maximum height, this point. So we'll call this H max. And its vertical velocity at this point is 0 meters per second. So let's answer this question. H max occurs at a vertical velocity of 0 meters per second. Uy equals to, how can we solve that? That's this component of the velocity u, uy. Remember, we solved this by resolving vectors. So uy is going to equal to 60 sine of 30. In other words, it's equal to u sine of theta. So we get that uy, the initial velocity in the vertical direction, is 30 meters per second. Ay is minus 9.81 meters per second squared. So again, I'm defining up as positive here and down as negative. So I can use the equation v squared is equal to u squared plus 2as, with all these components acting in the y direction. Well, v in the y direction is just 0, the final velocity, so I can get rid of that. And I can rearrange my equation to get it in terms of the displacement. Sy is equal to minus uy squared over 2ay. And I fill in all my values for that. So I have minus times uy is plus 30, all over 2ay, so 2 times ay is minus 9.81. So the minus is cancelled, and I get that Sy equals to 45.87 meters. But I have to add that 45.87 meters to the height that the arrow already was above the ground when it was launched. So in other words, that means that when the arrow is launched from this point in space vertically, it's going to travel up vertically through a displacement of 45.87 meters. But it was already 80 meters above the ground. So what's its vertical height above the ground, H max? It's going to be the vertical displacement plus the initial height, which is equal to 125.87 meters. Very easy to make a mistake here. So another thing that we could find, we could solve how long the arrow was in flight. Again, we're working vertically here, and vertically this is very similar to an example that we have in a previous screencast where a person throws a stone up in the air at the edge of a cliff and then it falls back down and falls down to the bottom of the cliff. Vertically speaking, it's the exact same. It starts off with an initial vertical velocity, it has an acceleration due to gravity, it reaches a maximum height with a velocity of 0, and then it accelerates back down in the opposite direction. So we can answer that question just the same. We can use the equation v is equal to u plus at. We don't know the time. Do we know the final vertical velocity? No, We don't, not yet. So if we look at where the arrow actually hits the person, we can say it's hitting them with a velocity, a final velocity v. And the final horizontal velocity vx is going to equal to the initial horizontal velocity ux, which is equal to u cos of 30, which is equal to 51.96 meters per second. And we're going to have a final vertical velocity vy. So think about the vertical displacement from here as it falls down until it hits the person. So in reality, remember, the arrow is traveling this arc, and then it hits the person in the chest with a vertical displacement from the ground of 1 meter, or a vertical height above the ground of 1 meter. So vertically speaking, all the arrow is doing is falling straight down. If we forget about the horizontal motion for a second, it falls straight down until it hits the person in the chest, and its vertical displacement sy will be equal to whatever the height of the cliff is, in this case 80 meters, minus the 1 meter that it is above the ground when it impacts. So in other words, its vertical displacement will be equal to 79 meters. We'll see that in a second. And it's also got a horizontal displacement, sx. So as I said, sy, the vertical displacement, is equal to minus 75 meters. Minus 79 meters. Why minus? Because it's traveling down. So I could use the equation v squared is equal to u squared plus 2as, and I can find the final vertical velocity. So the final vertical velocity is 49.5 meters per second. I know that it's a minus because it's traveling down. And now I can use the equation v is equal to u plus at to find the time. So initially I have to solve for the velocity, now I can solve for the time. So I rearrange my equation to get time on its own, and I get that the time is equal to 8.1 seconds. Again, be very careful when you're adding in all your values here. Vy is minus 49.5 and acceleration is minus 9.81. If you're not extremely careful with all your positives and minuses, you'll get the wrong answer here. So what distance should the target be from the edge of the cliff when the arrow is launched or released? So let's answer this. Well, we know that the arrow is going to be in flight for 8.1 seconds. So the question is, what horizontal distance is the arrow going to travel in that time? So here we're forgetting about the vertical, we're thinking only about horizontal. So we can use the equation s is equal to ut plus a half at squared in the x direction. What's its acceleration in the x direction? For projectile, the acceleration in the x direction will always be 0. So we can get rid of this, and we get that s is equal to u times t. So we fill in our values. Our horizontal velocity we got from u cos of 30, which was 51.96 meters per second, times a time of 8.1 seconds, and we get that the horizontal displacement is 420.88 meters. Okay, so we can see how these equations are very useful because they can be used in this case by the person launching the arrow to see exactly, knowing the velocity the arrow is released and the angle he's releasing it from, what distance his target should be away from the wall to accurately predict where the arrow is going to land. So we want to have one more example that we're going to cover. What if we had a cannon shooting a cannonball with a velocity u? And we know that that velocity is at an angle theta above the horizontal. So that velocity u is going to have some horizontal component, u cos of theta, and some vertical component, u sin of theta. And the cannonball is going to travel an arc and eventually hit the ground. So the cannonball is a projectile. It's going to hit the ground with a horizontal displacement sx, and we're going to call that the range. So that's the horizontal displacement that it travels. We call it the range. And another useful thing to work out, as we did in the previous question, would be the maximum height, or the maximum displacement in the y direction. So when given a question with just an initial velocity, u, and an angle, theta, nothing else, no time, no displacement values, we need to be able to work out the range and the maximum height. And we do that by deriving an equation for each quantity. So let's talk horizontally first of all. We know that the displacement in the x direction is equal to ut plus a half at squared, and because in the horizontal direction there is no acceleration for a projectile, we can get rid of the half at squared, so we're left with sx is equal to ux times t. But we don't have a value for time. So we're gonna first of all substitute our u for u cos of theta, because we're talking about the horizontal direction only. So our velocity, our initial velocity in the horizontal direction is u cos of theta times the time. But we have to pause here because we haven't been given the time. So we'll call this equation 1. And now we need to think about some way that we can substitute in an equation for time. Well, remember, time is a scalar quantity, and it doesn't depend on direction. So the time for the horizontal component is going to be the same as the time for the vertical component. So we can think about the time at different parts of the journey. So we're going to have to think vertically for a second here. And if we think about this time right here at h max, this occurs at a time of t over 2. Okay, assuming that the time t is the time for the complete journey, this maximum height will be reached halfway through the journey. In other words, at a time t over 2, or a half t. And we know that at this point, at a time t over 2, we have a vertical velocity of 0 meters per second, because at a maximum height, the vertical velocity is 0. So we're going to use the equation v is equal to u plus at in the vertical plane. So we're talking about Vy, which is 0, times u sine of theta, which is Uy, plus acceleration in the y direction, which is minus g, g being the value for the acceleration due to gravity, which is 10 meters per second squared, or 9.8 meters per second squared, or 9.81 meters per second squared, depending on which you decide to choose or which is given to you in the question. But in any case, we're going to choose that down as negative here, so the value for acceleration due to gravity is going to be minus g. And what's the time at this point? It's not t, it's t over 2. So we're talking about a point where the vertical velocity is 0. That occurs at a time t over 2. Okay? So we rearrange this equation to get u sine of theta by itself, and eventually then we can rearrange it to get time by itself. So we get an expression for time. T is equal to 2u sine of theta all over g. So if I sub the time into equation 1, I get that the horizontal displacement is equal to u cos of theta times, what was our expression for time? It was 2 times u sine of theta over g. So I sub in 2 times u sine of theta over g here. And I get that the horizontal displacement is equal to 2u squared sine of theta cos of theta all over g. But this value here, 2 sine of theta cos of theta, has a particular value in trigonometry. It's equal to sine of 2 theta. So I can rearrange this. I can substitute 2 sine of theta cos of theta for sine of 2 theta, and I simplify my equation to Sx is equal to u squared sine of 2 theta all over g. So this gives me an equation for the range, or the horizontal displacement, where I don't have any value for time. So what about our equation for the maximum height? Now we're going to talk about in the vertical direction. So we need an equation in the vertical direction which involves displacement in order to get the maximum height, but that doesn't involve time. So great, we already have one. V squared is equal to u squared plus 2as. And we're talking about the maximum height, which occurs at a final velocity of 0 meters per second. So in this case, Vy is going to equal to 0, so I can cancel all of this. So I get that 0 equals to, what's Uy? Well, Uy is equal to U sine of theta. So I'm going to get U sine of theta, all to be squared, plus 2 times, what's the acceleration? Minus g times sy. So I bring my minus 2g times sy over to the other side, and it changes sign, so I get 2g times sy is equal to u squared sine squared theta. I rearrange this to get sy by itself, and I have that sy equals to u squared sine squared theta all over 2g. So that's an equation for the maximum height that doesn't involve time. Okay, so if given a question where you're asked to find the range, in other words the horizontal displacement, or the maximum height, in other words the vertical displacement at a velocity of 0 meters per second, and you don't have the time, then you need to be able to derive one of these equations in order to solve that question. So you need to be familiar with these equations and exactly how to derive them. Okay? So that's projectile motion. You need to practice as many questions as you can on this. Refer to these screencasts if you get confused.